electrical systems, proper feeder conductor sizing and protection are crucial for safety and efficiency. Let's examine the specific example provided, addressing why a feeder conductor is based on 60 degrees Celsius and why the feeder protection is sized down. Firstly, the feeder conductor is selected based on the temperature rating of the equipment it supplies, in this case, the motor. Table 310.16 of the National Electrical Code, or NEC, provides ampacities for conductors rated 0 to 2000 volts. This table includes 2 columns for each American wire gauge, or AUG, size, one for 75 degrees Celsius and one for 60 degrees Celsius. The appropriate column is determined by the temperature rating of the connected equipment. Since the motor in the example is rated for 60 degrees Celsius, the 60 degrees Celsius column in Table 310.16 must be used to determine the conductor's ampacity. If the motor were rated for 75 degrees Celsius, then the 75 degrees Celsius column would be used, provided that all terminations are also rated for 75 degrees Celsius. The selection of the correct temperature rating ensures that the conductor can safely handle the current without exceeding its temperature limits. Now, let's discuss why the feeder protection is sized down rather than up. The key here is understanding the difference in the protection schemes for the motor and the feeder. The motor itself is protected by the branch circuit protection, which is sized at 2.5 times the motor's full load current, as per NEC guidelines. This high overcurrent protection setting is intended to allow for the high inrush current that occurs when the motor starts. The feeder, on the other hand, is protected by the feeder protection device, which has a different purpose. Its primary function is to protect the feeder conductor from overcurrents, not to protect the motor. The feeder conductor is sized at 1.25 times the motor's full load current plus the full load current of any other loads connected to the feeder. If the feeder protection was sized larger than the ampacity of the feeder conductors, it would not adequately protect the conductors from overloads. If you were to size the feeder protection too high, it might not trip in time to prevent the conductor from overheating and potentially causing a fire. The feeder protection must trip before the motor protection in an overcurrent situation, which is ensured by sizing it appropriately. The feeder overcurrent protective device, or OCPT, is selected to protect the feeder conductors. Its size is determined by following specific NEC guidelines. One common method involves summing the branch circuit protection devices for all the motors and other loads served by the feeder. This approach ensures that the feeder protection coordinates with the branch circuit protection. It allows for normal motor starting currents without nuisance tripping of the feeder breaker. The coordination between the branch circuit and feeder protection is essential. Branch circuit protection protects the motor and the individual branch circuit conductors. Feeder protection protects the feeder conductors supplying multiple loads. The goal is to have the branch circuit protection trip first under an overload or short circuit condition on the branch circuit, isolating the problem without interrupting power to the entire feeder. Now let's delve deeper into the calculations. The example states that the 5 horsepower motor has a full load current of 28 amps, and the 3 horsepower motor has a full load current of 17 amps. The branch circuit protection for the 5 horsepower motor is 28 amps times 2.5, which equals 70 amps. For the 3 horsepower motor, it is 17 amps times 2.5, which equals 42.5 amps. The next standard size up from 42.5 amps according to NEC section 240.61 is 45 amps. The feeder conductor is sized at 1.25 times the full load current of the largest motor plus the full load current of the other motors. In this case, it is 28 amps times 1.25 plus 17 amps, which equals 52 amps. According to Table 310.16, a number 6 American wire gauge, or AUG, conductor rated for 55 amps at 60 degrees Celsius is suitable. The feeder protection is calculated by adding the branch circuit protection for the largest motor to the full load currents of the other motors. In this case, it is 70 amps plus 17 amps, which equals 87 amps. The next standard size down from 87 amps according to common practice in the NEC is 80 amps. This ensures that the feeder protection will trip before the branch circuit protection in an overcurrent situation. So, the feeder protection is sized to protect the feeder conductor, and the branch circuit protection is sized to protect the motor. The feeder protection is sized down to ensure that it trips before the branch circuit protection in an overcurrent situation, protecting the feeder conductor from damage. In summary, understanding the temperature ratings of equipment and the purpose of different protection devices is crucial for proper feeder sizing and protection. The NEC provides specific guidelines for these calculations, and it is important to follow them carefully to ensure a safe and efficient electrical system. Remember, the goal is to protect both the equipment and the conductors from overcurrents, and proper coordination between the branch circuit and feeder protection is essential to achieve this goal. Now, let's consider some additional aspects related to motor feeder sizing and protection. Firstly, it's crucial to understand the different types of motor starters and their impact on the overall system. Motor starters can range from simple across-the-line starters to more complex reduced-voltage starters. Each type of starter has its own characteristics regarding inrush current and starting torque, which can affect the sizing of the feeder conductors and overcurrent protection. For instance, across-the-line starters, which directly apply full voltage to the motor windings, typically result in high inrush currents, often 6 to 8 times the motor's full load current. This high inrush current needs to be considered when selecting the feeder conductors and overcurrent protection to prevent nuisance tripping during motor starting. Reduced voltage starters, on the other hand, such as auto-transformer starters or part winding starters, reduce the voltage applied to the motor during startup, thereby reducing the inrush current. These types of starters can allow for smaller feeder conductors and overcurrent protection compared to across-the-line starters, while still providing adequate protection for the motor and feeder. Secondly, the National Electrical Code, or NEC, provides specific guidelines for motor feeder sizing and protection, which must be followed to ensure compliance and safety. Article 430 of the NEC covers motors, motor circuits, and controllers, and it outlines the requirements for conductor ampacity, overcurrent protection, and short-circuit protection. The NEC also provides tables and formulas for calculating the minimum conductor size and maximum overcurrent protection for motor feeders, taking into account factors such as the motor's full load current, service factor, and temperature rating. It's essential to consult the latest edition of the NEC and follow its guidelines when designing and installing motor feeder systems. Thirdly, the coordination of overcurrent protection devices is critical for ensuring the reliable operation of motor feeder systems. Overcurrent protection devices, such as fuses and circuit breakers, must be coordinated to selectively trip in the event of an overcurrent or short-circuit condition. This means that the overcurrent device closest to the fault should trip first, isolating the fault without interrupting power to the entire system. Coordination studies, also known as selective coordination studies, are often performed to determine the appropriate settings for overcurrent devices to achieve selective coordination. These studies involve analyzing the time current characteristics of the overcurrent devices and ensuring that they are properly coordinated to provide reliable protection and minimize downtime. Fourthly, the ambient temperature and directing factors must be considered when selecting feeder conductors. The ampacity of a conductor is the maximum amount of current it can carry continuously without exceeding its temperature rating. However, the ampacity of a conductor can be affected by the ambient temperature in which it is installed. If the ambient temperature is higher than the conductor's temperature rating, the ampacity of the conductor must be derated to account for the increased heat. Derating factors are provided in the NEC and are used to adjust the ampacity of conductors based on the ambient temperature and the number of conductors in a raceway or cable. It's essential to consider these derating factors when selecting feeder conductors to ensure that they can safely carry the required current under the expected operating conditions. Fifthly, voltage drop calculations are an important consideration when designing motor feeder systems. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause problems such as reduced motor torque, overheating of equipment, and malfunctioning of electronic devices. The NEC recommends limiting the voltage drop in feeder conductors to a maximum of 3% for power, heating, and lighting loads, and 5% for feeders supplying motors. Voltage drop calculation should be performed to ensure that the voltage at the motor terminals is within acceptable limits, and the feeder conductor should be sized accordingly to minimize voltage drop. Sixthly, the grounding and bonding of motor feeder systems are essential for safety and proper operation. Grounding provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices to quickly trip and clear the faults. Bonding ensures that all metal parts of the electrical system are electrically connected, minimizing the risk of electric shock. The NEC provides specific requirements for grounding and bonding of motor feeder systems, including the size of grounding conductors, the type of grounding electrodes, and the methods of bonding metal enclosures and equipment. It's essential to follow these requirements to ensure a safe and reliable electrical system. Seventhly, the use of adjustable speed drives, or ASDs, can affect the design of motor feeder systems. ASDs, also known as variable frequency drives, or VFDs, are used to control the speed of motors by varying the frequency and voltage of the power supplied to the motor. ASD can introduce harmonic currents into the electrical system, which can cause problems such as overheating of transformers and conductors, malfunctioning of electronic equipment, and increased energy losses. Harmonic filters may be required to mitigate the effects of harmonic currents in ASD-driven motor systems. Additionally, ASD can have high inrush currents during startup, which must be considered when selecting feeder conductors and overcurrent protection. Eighthly, the proper selection of motor overload protection is crucial for preventing motor damage due to overloads. Motor overload protection devices, such as thermal overload relays, are designed to protect motors from overheating due to sustained overloads. These devices monitor the motor current and trip when the current exceeds a certain threshold for a specified period of time. The overload protection device should be selected based on the motor's full load current and service factor, and it should be sized to allow the motor to start and operate without nuisance tripping. The NEC provides specific requirements for motor overload protection, and it's essential to follow these requirements to ensure that the motor is adequately protected. Ninthly, regular maintenance and testing of motor feeder systems are essential for ensuring their continued reliable operation. Maintenance activities should include inspecting conductors for damage, tightening connections, cleaning equipment, and testing overcurrent protection devices. Overcurrent protection devices should be tested periodically to ensure that they are functioning properly and will trip within the specified time current characteristics. Regular maintenance and testing can help to identify potential problems before they lead to equipment failures or safety hazards. Tenthly, it's important to stay up to date with the latest codes and standards related to motor feeder systems. The NEC is updated every 3 years, and it's essential to be familiar with the latest changes and revisions. Additionally, other standards, such as those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Electrical Manufacturers Association, or NEMA, provide guidance on the design, installation, and maintenance of motor feeder systems. Staying informed about the latest codes and standards can help to ensure that motor feeder systems are designed and installed in accordance with best practices. In addition to these considerations, it's also important to document the design and installation of motor feeder systems thoroughly. Documentation should include wiring diagrams, equipment specifications, calculations, and test reports. This documentation can be valuable for troubleshooting problems, performing maintenance, and making future modifications to the system. By following these guidelines and paying attention to the details, it's possible to design and install motor feeder systems that are safe, reliable, and efficient. Now let us delve further into specific NEC articles and tables related to motor feeder sizing and protection. The NEC provides detailed guidance on these aspects, and a thorough understanding of these articles and tables is essential for any electrical professional. Article 430 of the NEC, as mentioned earlier, is dedicated to motors, motor circuits, and controllers. This article covers a wide range of topics, including motor ratings, conductor sizing, overcurrent protection, control circuits, and motor control centers. Within Article 430, several specific sections are particularly relevant to motor feeder sizing and protection. Section 430.22, for example, addresses the minimum ampacity of motor circuit conductors. This section specifies that the conductors supplying a single motor must have an ampacity of not less than 125% of the motor's full load current rating. This 125% factor is intended to account for the motor's starting current and continuous load requirements. Section 430.24 covers the ampacity of conductors supplying several motors. This section requires that the conductors have an ampacity not less than the sum of the full load current ratings of all the motors, plus 25% of the highest rated motor in the group. This provision ensures that the conductors are adequately sized to handle the combined load of multiple motors. Section 430.52 addresses motor branch circuit, short circuit, and ground fault protection. This section specifies the maximum rating or setting of the overcurrent protective device, such as a circuit breaker or fuse, used to protect the motor branch circuits. The maximum rating or setting depends on the type of motor, the type of overcurrent protective device, and the motor's starting characteristics. Table 430.52 in the NEC provides guidance on the maximum rating or setting of motor branch circuit overcurrent devices for various types of motors and overcurrent protection devices. Section 430.62 covers motor feeder short circuit and ground fault protection. This section specifies the maximum rating or setting of the overcurrent protective device used to protect the motor feeder. The maximum rating or setting is typically based on the sum of the motor branch circuit overcurrent devices, with adjustments made to account for the diversity of the motor loads. Table 430.248 and Table 430.250 in the NEC provide full load current values for single-phase and three-phase alternating current motors, respectively. These tables are used to determine the full load current of motors for conductor sizing and overcurrent protection calculations. Table 310.16 in the NEC, as previously discussed, provides the allowable ampacities of insulated conductors. This table is used to determine the appropriate conductor size for motor feeders based on the conductor's ampacity and the ambient temperature. Annex B in the NEC contains examples of motor circuit calculations. These examples can be helpful in understanding the application of the NEC requirements to specific motor circuit scenarios. It's important to note that the NEC requirements for motor feeder sizing and protection can be complex and may vary depending on the specific application. It's essential to consult the latest edition of the NEC and seek guidance from a qualified electrical professional when designing and installing motor feeder systems. In addition to the NEC, other standards and guidelines may also be relevant to motor feeder sizing and protection. For example, the National Electrical Manufacturers Association, or NEMA, publishes standards for motor control equipment, including motor starters and overload relays. The Institute of Electrical and Electronics Engineers, or IE, publishes standards for electrical power systems, including motor protection and coordination. These standards and guidelines can provide valuable information and recommendations for designing and installing safe and reliable motor feeder systems. By understanding the NEC requirements, consulting other relevant standards, and seeking guidance from qualified professionals, it's possible to design and install motor feeder systems that meet the highest standards of safety and performance. Remember that electrical work can be dangerous, and it's always best to err on the side of caution. If you're not sure how to do something, don't hesitate to ask for help from a qualified electrical professional. Safety should always be the top priority when working with electricity. Now let us discuss some common mistakes to avoid when sizing and protecting motor feeders. These mistakes can lead to unsafe conditions, equipment damage, and code violations. Firstly, failing to consider the motor's full load current is a common mistake. The full load current is the current that the motor draws when operating at its rated horsepower and voltage. It's essential to use the motor's full load current, as listed on the motor's nameplate or in NEC tables, when sizing conductors and overcurrent protection. Using an incorrect full load current can result in undersized conductors or oversized overcurrent protection, which can lead to overheating or inadequate protection. Secondly, neglecting to apply the 125% factor to the motor's full load current when sizing conductors is another common mistake. As mentioned earlier, NEC Section 430.22 requires that the conductors supplying a single motor have an ampacity of not less than 125% of the motor's full load current rating. Failing to apply this factor can result in undersized conductors that are not capable of carrying the motor's starting current and continuous load requirements. Thirdly, oversizing the motor branch circuit overcurrent protection is a frequent mistake. While it's important to provide adequate overcurrent protection for the motor branch circuit, oversizing the overcurrent device can reduce its effectiveness and may not protect the motor from damage. The NEC provides specific guidelines for the maximum rating or setting of motor branch circuit overcurrent devices, and it's essential to follow these guidelines to ensure proper protection. Fourthly, neglecting to coordinate the motor feeder overcurrent protection with the branch circuit overcurrent protection is a common mistake. As discussed earlier, coordination between the feeder and branch circuit overcurrent protection is essential for ensuring selective tripping and minimizing downtime. Failing to coordinate the overcurrent protection can result in nuisance tripping of the feeder overcurrent device, which can interrupt power to other loads on the feeder. Fifthly, using the wrong conductor temperature rating is another mistake to avoid. Conductors are rated for a maximum operating temperature, and it's essential to use the correct temperature rating when selecting conductors for motor feeders. Using a conductor with a lower temperature rating than required can result in overheating and insulation damage. Sixthly, failing to consider ambient temperature and derating factors is a common mistake. As mentioned earlier, the ampacity of a conductor is affected by the ambient temperature in which it is installed, as well as the number of conductors in a raceway or cable. Neglecting to consider these factors can result in undersized conductors that are not capable of carrying the required current under the expected operating conditions. Seventhly, overlooking voltage drop calculations is another mistake to avoid. Excessive voltage drop can cause problems such as reduced motor torque and overheating of equipment. It's essential to perform voltage drop calculations to ensure that the voltage at the motor terminals is within acceptable limits. Eighthly, neglecting to properly ground and bond the motor feeder system is a serious mistake. Grounding and bonding are essential for safety and proper operation, and failing to properly ground and bond the system can increase the risk of electric shock and equipment damage. Ninthly, failing to properly document the design and installation of the motor feeder system is a common mistake. Documentation, including wiring diagrams, equipment specifications, and calculations, can be valuable for troubleshooting problems, performing maintenance, and making future modifications to the system. Tenthly, neglecting to stay up to date with the latest codes and standards is a mistake to avoid. The NEC and other standards are updated regularly, and it's essential to stay informed about the latest changes and revisions. By avoiding these common mistakes and following best practices, it's possible to design and install motor feeder systems that are safe, reliable, and efficient.